So let's talk about ML modeling or AutoML community about hardware, and that's sometimes different. And I thought about how to arrange the presentation. And after my conversation yesterday, I decided a little bit to put a little bit more tutorial style at the first half of the presentation, and then to go into a little bit more into detail. Probably it's helpful for you to have a better understanding what's actually happening in the hardware and what we have to take care about. Yeah, and yeah, somehow you're working on the left-hand side. You would like to optimize given ML models or even to find ML models. We are looking here to bring it down to hardware, and actually that's the next generation of NVIDIA, the broad architecture, the GB200. Yeah, that's a multi-chip solution, and it's very high performant, but yeah, it's probably not that good to bring that down into an embedded system. And you will not see that kind of GPU in a smartphone. Then you need a cooler, and even in a car, it's probably not that good. And I also shown here some kind of device we are interested in. There's a large time lag. I don't know. Then I have to do it here. And okay, we are focusing on that kind of video capsule, and I have it with me here. That's a capsule, and you can swallow that capsule. And yeah, and then your GI tract will get analyzed. Yeah? Then you would like to perform cancer detection. And no one wants to swallow a GPU from NVIDIA probably. But yeah, you need really ultra low power inference solutions, and that's one part of the story I would like to talk about today. How to get there? Yeah? What is needed actually to get a chip ready that's capable to deal with a number of ML models to get implemented on that. And that's means we need a lot of interactions, not to directly get back the application domain data to the model, but also to bring that back to architecture. Here's some kind of abstract architecture. We will see here some CPUs. We have a quad-core CPU, for example. It could be an ARM CPU or a RISC-V CPU. Here we have some NPUs, neural processing units, so that are AI accelerators, and here we have probably a smaller NPU. Probably we have here the always-on part of a chip that sends the data, take care about activities, that's an input, and if some activity is found, then that NPU will get activated to do some kind of classification task, for example. Yeah? And only if needed, you can switch on the CPUs, probably to communicate with the outside world. And so you have some kind of multiple wake-up levels to be integrated, and that device have to be ready to deal with different or a well-defined class of neural networks. We are not interested to have a one-by-one relation to optimize the design towards a single neural network. No, it have to be towards a family of neural networks. Okay, before getting there, I would like to discuss first some complexity issues. And yeah, probably you know already that slide. We have the complexity drawn here. First a blue of, I learned it yesterday, deep learning version 1.0 and red 2.0, yeah, and yeah, the classical deep learning CNN-based architectures in blue, and the foundation models, large language models in blue. And for years, a lot of people talked about Moore's law. Yeah? Moore's law tells you the chip complexity doubles every 2 years. Actually, it was in 75, John Moore corrected a little bit to 18 months, but later on it was again corrected to 2 years. Let's stay with that one. And a lot of innovation are actually based on that idea that we have exponential growth in chip complexity. Otherwise, it would be possible to have smartphones, for example. Okay, let's take a look to the blue ones, to the DNN area. yeah, we have a doubling every 3.4 months. And if we go further, then we see a doubling every 1 to 2 days in complexity. If we extrapolate the different models, then we have a doubling in complexity every 2 days. And yeah, and of course, Tübingen, we have a lot of ML colleagues in Tübingen, and they always told me, oh, Oliver, we just buy a new cluster and again, and then it will somehow work. But probably it's not a good idea to always follow that idea. Probably it would be good to look forward to smart deep learning, or probably also to go away from, let's say, brute force approaches here. Good. Yeah, probably you know that already. Some complexity discussion here in terms of GPT-4. It's a model of about 1.76 trillion parameters, and yeah, actually they are composing 8 models, each 220 billion parameters, and yeah, they are trained on 25 NVIDIA A100 GPUs, and in 90 to 100 days. Yeah, and yeah, and the energy cost for that training was about 53,000 megawatt hours, so it's quite high. Here I have a table with some kind of other models. It's taken here from the web page here on the right-hand side, and you will see, numbers also what is expected for GPT-5. It's known that for GPT-5 at least H100, but probably even better H200 or GB200 cards will be used, and rumors talked about 100,000 GPUs for doing that task. And yeah, it's probably not really sustainable approach to doing that. Here the costs are some estimates, the costs of training. Yeah, it's not possible for us anymore to train that kind of models. Of course, the hardware costs, but also energy costs are tremendous. Yeah, that's really a problem here. And with respect to sustainability, I have older numbers. Here numbers, I just picked GPT-3 in the middle here. Here's the energy consumption to train GPT-4. It was 1,287 megawatt hours, and then also the carbon dioxide footprint is also shown, so it's really significant. But I'm just talking about training, but yeah, also inference a problem. And yeah, if you make some estimates that are still older estimates, they are discussed 270 million queries per day, and 5 Q&A turnarounds in a session. And then the energy costs of 1 month of inference would take 18,720 megawatt hours. So it's much more than just for training. Yeah? And so we have to discuss that. And if you go to GPT-4, yeah, that's GPT-3, and that's the bar for GPT-4. It seems not to get better here. It's a problem. Yeah, and what about the chips? And probably the chips need also to get larger and larger. And NVIDIA actually does not build the largest chips. There exists a company, Cerebras. You know Cerebras? No one. Okay, that's a company here. And that's a single chip. You see here on the right-hand side a single chip. And it's the largest AI chip ever built, according to the advertisements of Cerebras. But it's actually true. They're talking about 4 trillion transistors, and it's built also with a TSMC process, as NVIDIA is doing. And yeah, inside the chip they have memory and compute together. Yeah, in memory compute, and that's provides very high performance solutions. But if you think all is getting better, then probably let's see what is happening. a single chip has a power consumption of 15,000 watt. A single chip, and they need a large number of chips, and they sell that already in larger devices. And the chip is on a card. The card needs to be somehow cooled, and the card has a power consumption of 23,000 watts, even more. And then, yeah, their claims they can really deal with large models, and they can build a cluster scale compute with up to 2048 of that kind of modules. Then you can calculate about the power consumption. But they can train GPT-3 in a day. That's cool, yeah? But it's even costly, yeah? That's a problem. And the utilization in terms of are very low. Yeah? If you usually you would like to have at least 80% of the manufactured chips to be ready for operation. And here they are talking about 10 to 15%. So it's very expensive to go in that direction. Yeah. Okay, that are some kind of complexity remarks here. Probably some have already been mentioned this morning. Then, machine learning for automated driving. I have some slides on the direction, just for the motivation. Yeah, of course, we are talking about that real hardware. Yeah, the cars with a lot of sensors equipped on a vehicle. But that's not our part here today. We would like to take a look inside. Inside we have an architecture of probably multiple central compute units, and they are built of several of the chips we just discussed. Yeah? Not CFRs, of course. And I don't want to teach automated driving, but I would like to just highlight automated driving is more than just perception. Yeah? And that's probably very often misunderstood. We have basically four basic blocks in a chain. One is perception, of course. The other is prediction. The next one is planning. And the last one is control. Yeah, perception means actually really environment perception, segmentation. To see here, for example, where the street, where you can drive on, where are obstacles, where are other vehicles, and so on. And then that's probably solved quite well. But of course, we have to take care about adversarial environment conditions, like difficult weather conditions, for example, that needs to be taken into account. Yeah, probably today it looks like California, but in winter it can look quite differently in Germany. But a very difficult task is prediction as well. Yeah? To predict what other dynamic objects will do. And that's probably easy for other vehicles, but it's not that easy for pedestrians, for example. Yeah? To have a prediction model, a behavior model of pedestrians, it's still very, very difficult to do. Yeah? And based on that, then we can start to do the planning. First the maneuver planning, and inside the maneuver the trajectory, and then we can start to control the vehicle, to do the vehicle dynamics. That means you have a lot of functions to be implemented and not a one-to-one relationship. And that's important here. And that's shown here on the next slide. So that means we have a large number of machine learning models running. We have classical software running on the system, and all needs to be mapped and executed on that kind of hardware architecture. That means we need also a runtime environment for machine learning models. Yeah? So we have to take care, when I have to read the sensor signals, when I can deliver the signals, in which period I have to consider the classification task, for example, for perception. And that's all scheduled in very fixed periods. And if we run different networks on the same chip, we don't want to run in a batch. Yeah, we have to schedule them, and then we have to take care where are the data in the memory, how they are mapped to the memory, and if the data are already available, if I would like to access them, there are a lot of important questions that needs to be solved. Yeah? And that needs to be considered with respect to energy demand. Yeah, we would like to minimize the energy consumption under latency constraints. Yeah? Okay, then let's just take one task. Let's say object detection task will be executed multiple times with different algorithms to do also some kind of plausibility checks. It's very important. Yeah? But let's take just a single task, and that's what a lot of people are doing to consider ImageNet, for example, as a starting point. We are talking about a resolution of 224 by 224, something like that. Yeah, and a vehicle we would like to go probably for full HD or maybe for 4K resolution, and that significantly impacts actually the complexity as well, just by considering a single function here. Yeah? And that's shown here. Yeah? If we took as example here very old networks, mobile net, ResNet, for example, and VGG, and then you see some kind of complexity considerations with the ImageNet frame. And that's shown here in that area. If we go ahead, what? And what's changed? Sorry, I didn't check. Yeah, here that's a consideration of a single image. So that's actually the status if you write your paper and you would like to bring results for ImageNet data set. No, I don't have to focus on single images. I have a video stream. I have to deal with 30 frames per second, and then of course the complexity will increase. Yeah, and probably I need also some kind of object tracking in the temporal axis. Yeah, and then if I have full HD, then I have even more complexity, and if I have multiple cameras, I'm here. Yeah? So that means the consideration in the papers are that one on the left-hand side, and the real stuff is that on the right-hand side. But we have to consider that for multiple tasks and not for a single task, and the multiple task could interfere. Yeah? That's also be possible. And in the end, we have some kind of solutions like this one. In a lot of vehicles, the trunk is full of compute. Yeah, you have a lot of servers included in the trunk of the vehicle. Even in the vehicles in San Francisco, if you would like to take a ride with automated taxis, it is even equipped with a lot of compute power. And yeah, that are conservative numbers, 4,000 watts. I heard, yeah, with cooling it's even more, it's 5,000, 6,000 watts. And if you have electric vehicle, and probably it's a good one which consumes only 40 kilowatts, yeah, then 1/3 of the energy is just for the autonomous driving. So then you have to think about, would like to take an autonomous ride? I would like to get to the final destination, yeah, with respect to the driving range. Yeah? And so it's really needed that you will end up with very energy efficient solutions in the vehicle. Okay, then it's an old chart here from 2020 about some ML accelerators. You see the x-axis peak power, and on the y-axis the peak performance. And here, there it is. Here's the stereo bus architecture with high performance. And actually, the best architecture would be high performance with less power, but there are not that many architectures, and so we have to think about to really deal with that problem. We have a lot of also academic architecture from MIT. The Iris architecture is a very interesting architecture, and that are very power efficient here actually. Yeah. Oops. Okay. If we take a look how to implement a system in a vehicle, then of course we have to think about what functionality will be deployed on central compute. that's shown here on the left-hand side, and what will be implemented on sensor-specific compute platforms. So that means the idea is to put more intelligence also into the sensors, and then you don't want to have large compute power in a sensor in terms of cooling the sensor and that stuff. No, you need some kind of sensor-specific solutions here. And in that area, in the green area, you can do a lot. Yeah, you can adapt your hardware together with your model. You can really apply co-design, AI system, hardware, software co-design to co-optimize the neural networks, the machine learning models together with the underlying hardware architecture. That's quite interesting. That's actually not possible on the left-hand side. COTS stands for commercial off-the-shelf platforms, that are more or less black boxed, and you have to take care about the resources that are available, and then you need to just probably use the vendor-specific flows like from NVIDIA. We have, for example, a cooperation project with Mercedes-Benz, and they are running more and more into trouble. They rely completely on NVIDIA with their level 3 support. But if they would like to further sell the cars in China, they have to switch away from NVIDIA. They have to find alternative solutions. And then, of course, you have to think about retargeting. How to retarget your model from one platform to the other one. And that's not easy. That from a model perspective is actually the case. Because bringing a model down to the platform to do the deployment takes a lot of effort. You have to do a lot of manual tasks. And so that means the retargeting is still an open question, and a lot of people are working in that area as well. And probably you can also bring that on a single chip solution consisting of multiple chiplets, and to package the multiple chiplets into a solution that can be composed of commercial off-the-shelf platform that you buy an NVIDIA chiplet and can put sensor-specific chiplets around, for example. And also some kind of safety critical cores. In every vehicle you have, for example, NVIDIA cores that's doing the safety critical stuff. Here's a slide from Mercedes about the terror operations that are expected for the different levels of autonomous driving. And we see that here towards level 4, we actually need terror scale compute. And they are also thinking about to have some kind of chiplet approach. And in a chiplet approach, you can actually compose, for example, a GPU from NVIDIA with a CPU from AMD and with a NPU from Zima AI or AI Motive or something like that. But of course, you have to convince all the players that the interfaces are compatible to doing that. Yeah? But that's an idea that's currently under discussion. And then you can go in different regions with different alternative setups here. If some kind of blacklisting is done, then you will kick off the GPU and will substitute it by another one, for example. Okay, that's the automotive domain. The other is more or less edge computing. Here I would like to go towards a well-defined system, for example, a sensor-specific solution. Yeah? And it's very often the case. A lot of companies would like to make the sensors more intelligent, more smart, and then it's good to not rely on a central compute activity, no, to bring that kind of compute power into the sensor device itself. And then you know quite well which task needs to be executed. And then you can really do some kind of co-optimization and co-design of the sensor compute hardware together with the models that needs to be executed here. And that was a graphic I shown before. And and think about the capsule. And if you would like to have to swallow the capsule, then we have to look for devices like this one. Then we need a very, very different regime. And then we are talking about video inference in less than 10 microwatts. And that needs to be somehow developed. And then you are very sensor specific to doing their job. And that's what we are actually also doing. And I have some slides at the end that shows a little bit what we can do here. And yeah, to doing that, we need to trade off between flexibility and area and power efficiency. And of course, a very flexible device is a NVIDIA GPU. And that's the reason why it's done for training. You have a very well explored flow to get from PyTorch or TensorFlow or something else down to the device. So it's very, very well settled. And on the other hand side, you can take a single neural network and can synthesize a hardware that's dedicated to that kind of neural network. But then, of course, you have the highest area and power efficiency, but at the cost of a very unflexible design. You probably can change some weights, but you cannot change the architecture anymore. So you need something in between. Here's the Tesla chip that's a little bit in between, but you can also think about how I can combine, for example, systolic area like this one. I will discuss it later on with some kind of SIMD architectures. I will discuss it later on to come with a best fitting device. And then here I have a flexibility. Then you can, of course, deploy a number of family of neural networks depending on the operators that are supported by that kind of architecture. And that's what we have to take into account. And for doing that, that's actually, in a nutshell, in a single slide, what we are doing at my chair, to do a lot of co-optimization techniques, to describe architectural templates, to do some kind of hardware neural architecture search. We will have later on the tutorial on that. That means how to combine the neural architecture search space with a search space that will be provided by the hardware, because your hardware model will also constrain your neural architecture search space. Probably not all operators are supported, or operators are supported a different, let's say, performance that needs to be considered. And for doing that, we need also some kind of performance model of the hardware architecture. Either the performance model of the hardware architecture you will develop, or for existing commercial off-the-shelf platform, it's very difficult to do some performance estimate without running your model on a hardware. And at the end, of course, you have to do it, but probably to do it in a neural architecture search loop, it's probably good to have a very efficient performance model that's doing the job. And then, if I found a good solution, then I need to deploy. And the hardware architecture without deployment capabilities is useless. You need a tool flow to deploy your neural network down to the hardware. Okay. So that was two examples, two application domains. One was the automotive domain, the other was the sensor edge domain. And this morning I thought a little bit about, should I directly dive into some kind of papers we have worked on, but probably I would like to bring something in between. So now I have selected some slides from my lecture about operators and about hardware primitives and how we can bring that together, then probably have a better understanding. Okay, so now we would like to, what's the idea? To consider the neural networks I would like to implement. I have to consider the operators I have to implement. I have also to consider the topology of the neural network, and also somehow the hardware that needs to be used. And of course, we need to support convolutions. And here I would like to go very, very quickly. and here's the loop nest of the 2D convolution, and at the end, what's important here in the middle of the loop nest, you find actually the operations. That's the MAC operations. You see that operation has four memory accesses, and 2 allo operation means the multiplication and the accumulation of the result. That means you need hardware like this one, yeah? Multiplier and some adder, and probably this result will be feedback to the input to do the accumulation. And if that can be executed in integer, then it's very easy. If it's a floating point, then you have to do a little bit more. Yeah? Okay, and then for small hardware, it's very good to think also about to reduce a little bit the complexity of convolutions. And here the depth-wise separable convolutions are very popular. There was introduced by the mobile network that's very successful in a lot of embedded domains. And yeah, what it means, you would like to if we start with regular convolutions, all channels are considered in parallel and have to apply the convolution across all channels and have to build the accumulated sum also about all the channels. And here the idea is to do the convolution separately for each channel, and then to somehow combine the result, apply a one-by-one convolution across the different output channels, and then hopefully I will end up with the same result. Actually, not really, but the results are very good in the papers. And if you compare the numbers here in the complexity, how many operations needs to be executed, here we are about 0,000 and we are here about 35,000. So just thinking about to deal a little bit with the operators can be very good. And if at the end the accuracy is at the same level, then of course it could be fine. No? And that's also part of the search space description. And to deal a little bit, to substitute convolutions by depth-wise separable convolutions, to deal a little bit with bottlenecks, that's what we have just seen here. Also inverted bottlenecks, NAC operators, where we can concatenate the result multiple times to enlarge the number of output channels. Yeah, fully connected, I don't have to spend many time here. It's actually basically a multiplication we have to apply here. I don't want to spend too many time here. Just batch norm layer, it could be difficult in hardware, but not during inference time. For training, it's complicated. I have to calculate all that stuff, the means and the standard deviation, and then the square root and so on. But a lot of numbers are constant, and then I need just to keep the constant in the memory, and then that can be applied quite well. But of course, we have to take mini batches. If I have to consider also mini batch for inference, for example, I would like to consider temporal access for audio, for example, then I have to think about to have some kind of moving window that calculates the standard deviation. And last but not least, of course, there exists much more, but I have limited time here. Let's take a look to transformers. There we have the self-attention mechanism, actually multi-head attention. And actually a lot of operators are well known. We have here the linear transformation for the query, for the key, for the value. That's quite good. And then we have to build a score. Here we have some, and then we need to scale. Scaling means we have to build the square root. But if we select the value well, then it's good. Here in the paper, they're selected to 64, square root of 64. Wow, very good. It's integer, it's 8. Division by 8 is just shifting by 3. That's cool. Yeah, that can be implemented quite well in hardware. But here, that's a killer. Here, the softmax. We don't like softmax as a hardware guys, and that's probably think about to have different operators like softmax to find more efficient hardware solutions. But also to deal with really large contexts is also difficult because you have to think about the memory consumption to hold all the data to apply the matrix multiplication. Okay, so that's the operator point of view. There exist many more, but just as a nutshell. Now the hardware design principles. Now I would like to slow a little bit down. And yeah, one idea is to just take the neural network, consider the operators. Here we have, for example, the convolution. And then, of course, we have Mac components inside just to connect the Mac components as shown here in your neural network model. And probably I need also some kind of interconnect in between, some register in between. Yeah, that could be the solution. But of course, you need a really, really large hardware. Nothing is reused. You have a direct implementation of your neural network into hardware. It's not that flexible. And if you have billion of Mac operations, then you need a billion of Mac units for implementation. So it's not the right approach. Okay, so we need some kind of parallelism. Yeah, one is coming from that what we just mentioned to apply some structured parallelism. That means, okay, actually, if I build a dot product, it's more or less a linear chain. I can do it a little better due to commutativity of the operations. Then I will end up with a number of trees to be executed. Here at the top level, I have the multiplication, and then I have the adder tree at the end, and I can have multiple adder trees, and then all will be executed in parallel, for example. Or I can remove that parallelism, and I can just do the accumulation here in a temporal order, and then of course you have a higher parallelism than this one. And now somehow I have to orchestrate. I have to have an idea when to apply some parallelism rule. Yeah? Okay, let's take a look to energy consumption, and that's the energy consumption is one very important aspect here. If you are thinking about to build a hardware architecture. Okay, here we have just normalized numbers. That means, okay, let's start with consideration that execution operation on ALU takes 1 energy unit. That's a starting point here, because I need to do the computation, but where to get the data that I can influence. If I can just apply local data access, or I do have to access the data from the outside memory. And that's shown here how this is related with respect to the energy costs. It's very cheap to access data that's directly available in the register of our Mac unit, for example, a processing element that deals with that. That's more or less the same cost, but it's fine. Then, if I have multiple processing elements, here the processing element contains the Mac unit usually, and here I build some kind of array of processing elements to perform convolutions, for example, in a very high-performant way. Then sending data from this one to this one, that takes 2 times the energy of just calculation at a processing element. Then to access a buffer here, it's approximately 6 times the energy. And to access a DRAM, it's 200x. 200x more expensive in terms of energy. And that's the reason why a lot of people think about, okay, how I have to orchestrate the data to the memory hierarchy, to move the data in a way that are available in the right point of time, and I would like to reuse the data. If I know I have to reuse the data, then it's not a good idea to always access the DRAM. Then probably it's better to keep the data in a register. And so that's the idea. So that's one aspect. Just considering where to take the data from. Next aspect is quantization. Quantization is also very related to energy costs. And that's shown here, but on the right hand side, the energy cost of operation with respect to different data types is shown here. Here on the top we have integer add operations in 8 bits, 16-bit and 32-bit. And you see the energy costs in picojoule. Then the next one is floating point add. Floating point is much more expensive than integer. Then the same for multiplication. Multiplication is more than addition, of course, and floating point is even more. But again, getting data from memory is also very expensive. And we have to take care, probably to reduce also the data word length that needs to be integrated in memory. And then, if I would like to do our computation, then probably it's good to think about, should I calculate with 8-bit integer or always or only sometimes, and when it's actually needed? And actually the quantization applies it a little bit differently, and that's quite interesting here. And so it's quite good. Let's start to think about going from floating point 32 to integer 8. So that's the idea. And usually you have some input values and some weights. And then here at the crossing point, you have your MAC operation that multiplies the weight with the input and accumulates. And the accumulation can also be passed in that way, but also passed in that way, and that's possible. And then we have to think about, it's good to have all data in 8-bit. Well, good ideas, that solution exists also theoretical concept behind that. To have actually 8-bit integers, 8-bit weights, then the memories are also used much more efficiently, but it's not that good to do the accumulation 8 bits. Then at the end, you will not see some kind of difference between the results, but a lot of significant digits are somehow shifted out. And so the idea is to do accumulation 32 bits, and then at the end I have to re-quantize to 8-bit to bring it back to the memory, and that's a quite good approach. Then the costed multiplication takes 8-bit, 8 by 8. The accumulation takes 32 bits, and all memory accesses are in 8-bit, and that matches quite well the energy consumption here on the right-hand side. And that's also approach that, for example, that NVIDIA is following. Good. Next. That are some data types. I don't want to spend time here. If you have questions afterwards, I can spend time here. So now reusing the data. How we can orchestrate temporal and spatial reuse. And let's start. Of course, memory accesses. We learned that memory accesses are expensive, but we somehow have to calculate the data. We see, in ResNet 18, for example, we have 1,800 million max. In MobileNet, we have 330 million max. And that will result in that numbers of memory accesses if we don't do anything. And the very easy approach is to put some memory hierarchy in between to apply reusing the data. And of course, this memory will be smaller than that one. And like a cache, actually like more a scratchpad memory, we have to know when data are available. And that's very important to do that in an efficient way. Spatial reuse, we could, of course, unroll a loop. If we unroll the inner loop of our loop nest 4 times, then we have have a parallelized structure at the end of 4 MAC operators that are running in parallel. But of course, if we do that, then we will see that probably to all data can be fed the same input data, the same weight, depending on the operation you are considering. And if all the same weights are available, then of course you can reuse the data by just interconnect them directly. And so that's a baseline to discuss a little bit the data flow. To discuss the data flow in a machine, and there exists well-defined terms to orchestrate the data flows, and a lot of architectures are following that idea. One idea is do nothing. No local reuse, and all will be accessed all the time directly, and then probably you will have different weights, and at each processing element you will have probably sometimes the same input activation, sometimes not. You will sometimes have the same partial sums to be propagated, sometimes another one. It's completely useless to consider the no local reuse approach. One is to think about the weights, and that's called weight stationary. That's a reference pattern. I can reorder the loops in a way that the weights will get stationary. That means here you see the memory accesses that are used to access the weights in the memory, and you will see, okay, multiple times the same weight address will be taken, and that 4 times. So then we have jump to the next one, and then can access 8 times the same value. And in that patterns, of course, if you use this pattern, then you have to take into account, probably it's good that you have a register in your processing elements that keeps your weight value, and then you can always access the internal register, to deal with that pattern in an efficient way. A lot of architectures are following that idea, but it's not all that you can do. That's a pattern at the end. Here you have a multiple accumulate unit, and then the weight registers here in between, and then can access multiple times the same value. And here's a partial sum you have to think about to accumulate internally or to accumulate across the different MAC units. That could also be possible. Next, output stationary. Here you see, okay, I have just by reordering the internal loops of our convolution operator, for example, I have different patterns, then I can access the outputs multiple times. How to do that at the end? That's very easy. I put an output register in the processing element, and that output register will get feedback to the MAC unit. And then of course I have here more sequential operation, but I can also think about to do some parallelization. And that's a pattern here at the end that comes out. A lot of architectures are also using that pattern. And last but not least, input stationary. Here I can reorder the loops again, and then I can access multiple times the inputs. And then here I have also an internal register for that to do some reuse here. And if you build your architecture, you have to think about, okay, what kind of reuse mechanism I have to apply. I can also combine the different mechanism, and that's a very important aspect to increase data reuse and to decrease the energy demand. That's a well-known classification of parallel computer architectures according to Flynn. And so that's a standard CPU here, a single instruction, single data stream. And for machine learning architectures, we have very often a SIMD approach. That means you would like to apply the same operation onto different data, or the multiple structures, the single data stream architecture that's shown here, where I can apply multiple instruction to a single data, different point of time. Here it's more like a pipeline version of execution, and that's baseline also for systolic array. Can I also have multiple instances for that? Of course, I can, on a higher level of granularity, I can deal with multiple cores to do that, and then we are on the right-hand side. That's SIMD array processing, just to have a single MAC operation applied to multiple data. That's very easy. Here you see that if you have 4 data words I can access, I can directly apply it as a single SIMD operations. So the systolic arrays are shown here. We can think about to go more for a weight stationary approach or output stationary approach in the processing elements, and then we can think about when to pass the data around, when to propagate the data, and what will be executed internally, and that needs to be orchestrated. If I map my operator, I need to know how many processing elements I use. If I have not that many as needed, then I have to go in a temporal domain to complete your operation. And I will skip it. Okay, coming to NVIDIA. There was also a lot of questions. That's an H100 GPU as a fully equipped. There exist different versions, depending on if you have a PCI, NVLink version, and so on. And you have a lot of streaming multiplier processors, actually 144. And if you take a look into a single one, then you see that you have a lot of shader cores available. The shader cores are working according to a SIMD principle, to apply a single operation multiple times on different data. But also you have tensor cores, and that's quite interesting also for our idea here, actually to implement a matrix multiplication efficient way. It means in each of the 144 streaming multiprocessors, you have 4 tensor cores. Let's take a look into the tensor cores. I will come back to the memory. That looks like this one. You have the mapping of the 4 tensor cores to that kind of construct. And in principle, in each, I will not say clock step, but in each step, there will be executed in parallel an entire matrix multiplication with the data that are available. Here you have the data, here you have your data, here you have the data. So that means you have the cyan matrix A and the violet matrix B, and the result is in green at the end. And then, of course, you have to think about how large are my matrices, how they can map to the tensor cores, and here I can access the data very efficiently. I have local registers, but if I have the rest of matrix in some of the other streaming processors, I'm running into trouble. And that's a problem that needs to be orchestrated as well. So that's the execution model for floating point 16. If I go to floating point 8, that's good. I can use a 60-bit engine, can divide it by 2, and then I have 2 times the throughput. And that's shown here. That's actually the same hardware, just used for smaller word lengths, but 2 words can be executed in parallel. That's the idea here. Okay, then if I would like to go to an automotive solution, then NVIDIA provides Jetson Urban platform, and there you find more. There you find all the number of ARM GPUs. Then here inside is that what we have seen so far. Where there you have the tensor cores and the shader cores, but also a lot of other stuff. To deal with all the sensor aspects you will have in your car. That's a Tesla chip, and here they follow a little bit other approach. They follow a little bit the systolic array approach. Here we have 2 systolic arrays of 96 by 96 MAC units, but also the GPU SIMD approach. Here you have a number of ARM CPUs, And so that's the idea how the system is orchestrated. And the block diagram looks like this one. Here you see that you have the one of the MAC arrays of 96 by 96. And at the end you have your SIMD lanes. And here what's interesting is here the address generation. Yeah? They put a lot of effort in designing an appropriate address generation unit to have always the data at the right point in time. So that's the idea here, and that's a very, very beneficial aspect of that kind of tensor architecture, Tesla architecture. Yeah, and here's a Qualcomm version. Yeah, and there exist many more, and we have to deal with that. We have to deal with very different architectures. We have to know how large are the MAC arrays, how large are the memories, and if we take that into account, then we know how we can modify, how we can optimize our neural network for implementation. Yeah? That means hardware NAS, yeah, to take that into account. Yeah? Now we would like to optimize, and here I have a slide that's from Yuan from Tsinghua University, and he showed a bit about the optimization potential. He tried to efficiently implement large language models, and he started with algorithmic optimization. That means he had to perform some parallel decoding. Yeah? I have to really think about how to modify the transformer that I can execute parts of them in parallel. That's a manual task. He didn't show the hardware enough, but then he applied pruning, quantization, kernel optimization. Yeah, of course, I would like to implement the kernel in an efficient way with respect to the underlying hardware architecture, and then at the end to optimize, find optimized mapping to hardware. And you will see, without optimization of his work, you will have at each level 2 to 3x less performance illusion at the end. That's also the idea we follow. A little bit differently, we have some kind of system orchestration at the beginning. We need some to schedule design, to do some kind of memory considerations. And then that's what we will show afterwards, to do hardware NAS, yeah, with implicit or explicit pruning or some quantization. Then you can do the kernel optimization, optimize hardware mapping. We put a lot of effort in the deployment aspects, but we don't have time to show that today. What does it mean? Can I steal some time from the
team member? Yes.
Okay. Good. Then yeah. So system orchestration. Now we have the entire network of neural networks together with classical softwares to consider, and then we have to think about how I should map that on a device. And modern hardware architectures offer slicing capabilities. That means, I can assign models to different slices. I can also assign memory locations to decrease the interleaving problem, to decrease inference between the different parts. Yeah? And then, of course, I have to also schedule the design with respect to the periods. I have to execute in a task in a given period. I have also to consider that. For doing that, we have some kind of formalization. That's Patrick's work. Where describe data access patterns. It's not good to just rely on single data words. We would like to access the data access pattern, because if you know your operators of your ML model, then you know which data will be accessed next. And that can be described and used for optimization. But the starting point are the sensors. And that is fixed. Yeah? If you have a camera, then probably the camera parameter tells you the period. Here, this one is a fast one, which gives you oh, sorry, this one is a small, slow one with just 30 frames per second, and this one is a fast one with 16 frames per second. That means I need to execute my model afterwards with a frame rate of 60 frames per second, otherwise it would be possible. And here I have a leader sensor that has some kind of other patterns, and here I have inertial sensors like a gyro, accelerometer, and compass, a magnetometer that needs just to be accessed in 1 frames per second. And then I can also think about, okay, I have different AFI functions of my network, and I can map that to different devices. Probably I have here a neural processing unit 1, here a GPU, here a CPU, and so on, and then can do the mapping of the functions. And then each function provides again data access patterns, and they can take into account if they are compatible or not compatible. You see a row by row delivery of the data, and you have some kind of plugging, some kind of blocked tied approach to access the data. For example, if I apply the convolution, and depending how these patterns are compatible or not compatible, I can extrapolate the number, the memory size that needs to be used for the buffering in between. And that needs to be executed for all different parts in the system. And then I can optimize the entire architecture in a way I can find optimized memory sizes in the middle, for example, to find an appropriate streaming buffer. Yeah, in a way that the other components does not wait for completion of the first component. No, if I have already data in a blocking way available, I can start execution earlier in a pipeline manner. That's only possible if I have that kind of data access patterns at a system level available. Next is what we are showing in the tutorial, in hands-on, to do actually the hardware where NAS, and very important is the search space definition. And we have some kind of hierarchy here, how to define the search space. Here we have some kind of, let's say, macro architecture or macro topology of our module, of our networks in mind, which can sort of consist of multiple numbers of blocks. Each blocks can have different characteristics. Here we can put in a residual block or just linear block, and that can be selected and chosen automatically. Then inside you can also choose between different operators, standard convolutions, that kind of depth-wise convolution, bottlenecks, and so on. All your operators you would like to see there, you can define. Then if each operator can be refined further with respect, for example, kernel size, strides, number of channels, and so on. And you need also, that defines a neural network search space, and you have to do the same for the hardware, and then you can put them together, and that's the idea of what we are proposing. But of course, you need performance estimates, and that take care about performance. For the ML community, performance tells you probably accuracy. For the hardware community, it tells you latency. But we have to be aware about that. Probably it tells you about latency, energy, area, memory footprint. You need that metrics as well to evaluate your network. That's very important. And then that's the setup of HANA. I don't spend time here, you will expand later on. Last but not least, that's good. What we can do for edge devices. Here would like to have well-tailored devices. That means, okay, I would like to find also an appropriate platform for doing that. That's what Paul is doing. And to have some kind of architecture templates. And that architecture templates will be selected with respect to the family of neural networks you would like to implement. And with respect to the operators that in that kind of families are needed. With respect to, for example, convolution sizes. If a convolution size does not fit to this systolic area, it's probably not that good. And then, based on a generator-based approach, you will get an architecture and a deployment tool to bring a neural network down to the architecture. Then you can do some kind of modification in a loop to end up with a design space here. And then you can find for best suited solution at the end. And then you can tape out a chip for that. Yeah, that's what I have already discussed before is applied in that idea. All that kind of different optimization steps. And here you see some kind of macro architecture. Here you see all some kind of MAC array in the middle with some kind of local memory. Then you can decide, of course, the size of the MAC array. This is 8 by 8, 16 by 16, 4 by 4, or even more. Then you have also to decide how many registers we have to put inside the MAC array to do some kind of pipelining. Then, of course, how many local memories you would like to support, or do we have just a global memory that's not shown here? Here we have 3 feature memories, for example. That means you can deal very efficiently with residual passes. That means you have input memory, then a memory for the input feature map, memory for the output feature map. And if you have a linear pass, then the role will change next time. Then that's the input feature map the next time, and it's the output feature map. And if I have to support a residual path, I need additional feature memory, for example, to keep the data for the residual passes. Yeah, and that can all be configured in an automated way, and that's the cool stuff here. And here, that's, for example, a solution for multiple application or execution of 1D convolution. That was for audio use case here, for example. And then actually, that could for our audio chip, we just need 8 by 8 MAC array, and then you can run 8 1D temporal convolution in 1 clock cycle. That's quite efficient then. Yeah, and here that's some kind of description about that architecture, and then you can compose a larger system out of different instances of that architecture, and then you will also consider the neural network for that audio use case. That we wanted to apply a class of temporal convolution, ResNet-based architectures in the end with early exit possibilities, and that's shown here. I will speed up a little bit. Then you need some kind of models to determine the latency, to determine the power of your device based on architectural templates. Then you describe what parameters what parameters I can mutate. Here I can decide about how to constrain the parameters, how the MAC array sizes will be constrained, for example. What are the strides, and so on. And at the end, you will have that kind of design space. And what's interesting here, we have 3 different neural networks explored in parallel. That means CLUE stands for the audio use case keyword spotting. Orange tells you the data for voice activity detection, and green wake word detection. The area that's needed for hardware implementation is shown by the diameter of the circle. And the x-axis tells you the power consumption in microwatts, and here's accuracy on the left-hand side. And then you see, here's the yellow one, very, very low power solution, and that's very helpful because we start with voice activity detection first before to get to the next layer. And I will pick up some points here. We started with a manual design, and it was a TC ResNet architecture chosen with a word width of 6 bits. That was enough. We could quantize the 6 bits. Of the weights, and of the features 8 bits. And the MAC array size was 8 by 8. And then you see you will end up with accuracy of 93% and a power consumption of 8.2 microwatts. And if you apply that kind of architecture search or co-design together with the hardware, then you can see yeah, that you can halve the power consumption just by applying the automated tool. And yeah, and you will see the accuracy will more or less get the same. Yeah, but also you can also increase the accuracy with a little bit by a little higher power consumption. That's quite interesting, and that was a showcase that it's really possible what we are thinking about, and that's shown in the chip. That was done with at the end with in a project with Porsche and Audi with multiple wake-up levels. The idea was an always-on detector. If the driver gets to the vehicle is parking, then hey, it's me. Please open the trunk, for example. You can tell, and you have to have the voice activity detection. You have to detect the driver. You have to detect the keywords, and that does not need to high power consumption. Otherwise, if you park for two weeks and a lot of pedestrians are walking around, then your battery gets empty at the end. And that was a macro lecture. Here you have the always on unit, level 1, level 2, 3, 4. At the end, the CPU, which can communicate with the rest of the vehicle. And then that was a tape out, the architecture that was chosen. And the processor itself could be executed in 1 gigahertz. But the accelerator itself was just executed in 250 kilohertz. It can get more until 250 megahertz, but it was not needed. It was just enough for real time, and that's quite good. And then here's an evaluation board at the end. Yeah, the next step we would like to use the same for the capsule to do the video inference, and all the tooling. What we will see afterwards will help us here. And it was too many slides, I think. And now I'm at the end. Thanks a lot for listening. And it was a lot of hardware in a nutshell.